Okay. Good morning, everyone. It's my pleasure to introduce Novi Bong. Novi is from University of Delaware, and she will be speaking today on the degree diameter problem and maximum degree diameter bounded subgraph problem. Thank you.
Thank you, Sandra, for the opportunity, and then thank you, Nadia, for the introductions. So today I'm going to give an overview about degree diameter problems and the maximum degree diameter bounded subgraph problem. So the talk today has the following outline. The degree diameter, the upper bound of the problem, the lower bound, and then I will introduce what it means by maximum degree diameter bounded subgraph problems, what are the noun results, and then I will elaborate more on the maximum degree diameter problem on balanced network, and also give an introduction to the problem of hyperdiamond. Okay, so to start with, here are some terminology of graph theory. Probably most of you know about it, so I will go through it very quickly. A graph G consists of a set of vertices and the set of edges. And the order is just the number of vertices. The degree is the number of edges attached to a vertex. And then a walk of length t is a non-empty alternating sequence of t edges such that any two consecutive edges share a vertex. And the path is a walk with all vertices are distinct. The distance between vertices u and v is the length of the shortest path between them. Okay, so the number of edges of that connect the vertex u and v, and the diameter is the longest distance between any two vertices in the graph. Okay, so the neighborhood of a vertex is the set of all its adjacent vertices. The adjacency matrix is represented by a square matrix, all the rows and the columns labeled by the vertices. And then you have a 0 if there is no edge between the two vertices, and you give a 1 if there is an edge. Since we are talking about the simple graph, the entry of the matrix is just 0 or 1. Okay, so as you can see here, V1 to V2, there's an edge, so you put a 1 here, and V1 also connected to V5, so you have a 1 here. And as you also notice that all the entries in the main diagonals are zeros because there is no loop in this graph. Okay, and the square of A, which is this given matrix here, the entry tell us the walk of length 2 from vertex Vi to Vj. So in this case, if you look at V1 to V3, there's two ways to reach from V1 to V3. There are two ways to reach that. So with walk of length 2, you can go through this, or you can go up there and then come back down here. So you have a 2 here in the matrix. Okay. Right now you see at the main diagonal entry, it's no longer 0. But this entry tells us the degree of a vertex. So V1 can be reached by a walk of length 2, basically by every edge that it has. So if you go to this, you go up there and then you come back. So that's a walk of length 2, and it returns to the original vertex. Okay, so all of these main diagonal give you the degree of the vertex. Now, in general, if you raise the power adjacency matrix to t, all the entries give us the number of walks of length t between vertex I and vertex j. The trace of a matrix is the sum of the elements on the diagonal. And the trace A is 0, and then the trace A squared in this case is 16, is 2 times the number of edges here, because that's the sum of the degree. Now, the degree diameter problem comes up from the design of computer networks and also the parallel processing architecture. The question was, if each node connects to no more than big delta other nodes, how many nodes can there be in a network such that no two nodes are separated by more than d step? So you have a limitation of the connection for each node, but then you also want to try to reach as far as possible. Okay, so formally, this problem was formulated as following. Given a natural numbers, big delta and capital D, find the largest possible number of vertices and delta D in a graph of maximum degree, big delta, and diameter is at most D. Okay, so this is the maximum degree, this is the diameter. Here is an example. When we have the maximum degree is 3, the diameter is 2, then the maximum order that we can have is 10, and this is a famous Peterson graph. Okay, so there's a good survey about this problem is by Mirka Miller, who is my supervisor. She passed away in 2016, and Joseph Siran. So this is a dynamic survey. So more bound and beyond. I think this is the latest version. It's not updated anymore. Okay, so Electronic Journal of Combinatorics. Now, so what is the upper bound for this problem? If you look at the maximum degree equals to 1, then the diameter can only be 1. Okay, and then we have the order is 2. Okay, so we assume that the maximum degree is, oops. So when the maximum degree is greater or equals to 2, so D is greater or equals, the diameter is also greater than or equals to 2. We want to see how much entries that we can have in this problem. So we start with the rooted trees, okay, from a vertex, and then because of the maximum degree is capital delta, so you can go up. You can be connected to delta vertices, and each of the vertex and the level 1 can be connected to delta minus 1 vertices below it. Okay, and you keep going until you reach the diameter. So ideally, this is the maximum if you can. But the problem now is that, okay, from this vertex, it reaches everybody in D steps. But what if this vertex here? So we have to play with the connection at this level. How do we connect the vertices here such that every vertex reach every other vertices in D steps? Okay, because we want to keep the diameter to be D. So if we sum this from the tree, so we start from a root, so 1, and then you have delta vertices at the level 1. For the next one, you keep multiplying with delta minus 1, and then until you reach the D level. So if we sum this, we have 2 result. If you have delta equals to 2, then it's just 2D plus 1, or if delta is greater than 2, this is the upper bound that we have. This bound is known as Moore bound. Okay, so then graphs that achieve this bound are called the Moore graphs. Now the question is, do Moore graphs exist? I mean, this bound is there, but do we really have a graph that could achieve this bound? Okay. So there are 2 approaches for this problem. One of them is to show the existence or prove the non-existence of the Moore graph, and the other one is constructing the Moore graphs. So one is from the lower bound, you improve it. The other one is working from the upper bound. So here is a Moore graph of diameter 1. We can try to look at it how from diameter 1. So we start from the root, and then we can have 3 edges, 3 connections, because the max, for example, we take the example that maximum degree is 3. So we have this, and then we have to connect these 3 vertices here. How do we connect them so that they reach everybody in one step? Okay, so the result is a K4 complete graph on 4 vertices. And in general, if you want to have the diameter 1, the maximum degree big delta, then the Moore graph is a complete graph, K delta plus 1. Okay. And we move to the diameter 2. So if you have diameter 2, that means we start from a vertex, and then you have delta vertices, and then for the second level, you have to delta times delta minus 1 vertices. So if we sum this, we have 1 plus delta square. Because of its being diameter 2, it also means that all vertices can be reached by any vertex within 2 steps. So how does it look like? Suppose G is a Moore graph. Suppose that the Moore graph exists of diameter 2, and let A be the adjacency matrix of the graph. Okay, we represent the graph if it exists in terms of A, and then we know that because it has to reach every other vertices in 2 steps, then we have the following equations. So A squared is the walk, tells us the walk of length 2 from one vertex to another, and A is the adjacency matrix. Remember, in A square, we have at the main diagonal, we have the degree of the vertex, right? So here, since the degree is big delta, so we have big delta in the main diagonal of A square. So if we subtract away delta minus 1 times the identity matrix, it makes the main diagonal to be 1. All of them become 1. Okay, so if we sum this, we get the J, the matrices of all ones. Okay, so now we look at these equations. This is a work of Hoffman and Singleton in 1960. So the eigenvalues of J is n with multiplicity 1 and 0 with multiplicity n minus 1. So let lambda be an eigenvalues of A. So we have this following equation that it has to satisfy. 1 plus delta square equals to n. And then delta square, lambda square plus lambda minus delta minus 1 has to be 0. Okay. Solving this equation, it gives us that the lambda 1 and lambda 2, it's in this form, minus 1 plus minus square of 4 delta minus 3 over 2. Okay. So the eigenvalues for A, there are three choices. So one of them is the capital delta, because it's a, and then the lambda 1 and lambda 2 is here. Okay, so what do we know? What can, so for lambda 1 and lambda 2, given like this, and we know that the trace of A is 0. The trace also gives us the sum of the eigenvalues. So if lambda 1 and lambda 2 are irrationals, and to add up to 0, that means that they should have the same multiplicity. So n minus 1 over 2, lambda 1 plus lambda 2, we sum all of this, and we get to 0. So what is the possible value for delta? The delta is either 0 if we solve this, which is impossible because we are talking about the diameter 2. If you don't have any edges, then it won't be a diameter 2. And then when delta is 2, then you get a cycle of length 5. Okay, so this is diameter 2 as well. The other possibilities is, what if lambda 1 and lambda 2 are rationals? Okay, so if it's rationals, it means that this number under the square root is a square number. So I assume this is called the s square. So we have the following: delta is s squared plus 3 over 4. So if we sum this, assume that one of them has multiplicity m, then the other should have n minus m minus 1. Solving this, Hoffman and Singleton actually give us, these are the possible values for the maximum degree, and this is the order of the graph. Okay, so when the maximum degree is 1, the order is 2, but this one doesn't give us the diameter 2. It's just a K2. Okay, and when delta equals to 3, order equals to 10, we have the graph that is Peterson that I showed you in the beginning. Okay, and when the delta equals to 7, and this is actually the Hoffman-Singleton graph, it has 7 vertices, sorry, it has 50 vertices, and then the degree is 7. The other value that we have, if you look at the table, is the degree of 57, and then the number of vertices is 3,250. This remains open, okay, until today. What people do is they try to understand the structure of the Moore graph of degree 57 if it has 2 axes. Okay, if Hickman in 1960s tell us that the Moore graph of degree 57 diameter 2 cannot be vertex transitive. Another result is that it's not a graph of rank 3. And they also study the automorphism group. There's also a result by Mackay and Siran in 2010. The most recent update of this problem, I think that I could found is that I'm aware of is this paper by Juricic in Vidali. They said that if delta, let delta be an integer, this is the result of their paper that can be related to the Moore graph. So the following statements are equivalent. So if a Moore graph M of diameter 2 and the degree delta exists, it is equivalent that there exists an antipodal distance regular delta -1 coverage of the complete graph KR, or there exists a distance regular graph sigma with intersection array like this. Okay, so that's all about the Moore graph of diameter 2 that we know. And then what if we increase the diameter to be more than 2? So the similar technique is used, and we use the eigenvalues. Okay, so then but in this case, when delta equals to 2, the Moore graph is just the odd cycle. And Hoffman and Singleton in that paper, the previous paper, they also showed that the only Moore graph of diameter 3 is the graph with degree 2, so which is the C7. Okay. So now we for maximum degree greater than 2 and the diameter greater than 2, no Moore graph exists. And this is done by Damerel and also independently by Bana and Ito. Okay, so Moore graph business is the remaining open one is the 57, the degree 57. Okay, so then what do people do? They try to see. I mean, Moore graph is a large graph, so they try to see whether it's possible to get something close to Moore bound. Might not reach the Moore bound, but what if it's some number less than the bound? So they introduced the almost Moore graph. So in general, they have the M, which is the Moore bound, minus delta, which is called the defect. When delta equals to 1, that's what it is called almost Moore graph. So when the diameter is 2, almost Moore graph exists only for delta equals to 2. And the graph is the C4. This is the result of Erdős, Vajtlovic, and Hoffman. Okay. Then when the diameter is greater or equals to 3, almost Moore graph exists only for delta equals to 2. And the graph is the cycle, the even cycle. This is the result of Bana and Ito, Kurosawa, and Tsuji in 1981. And then also prove that almost Moore graph do not exist for delta greater than 2 and the diameter greater than 1. Okay, so what's next? There is something called the almost Moore graph. So when the defect is 2, then you have 2 almost there. So don't worry, they don't continue with this term. They don't have almost, and so on, okay? So they stick with the defect after that, okay? Is it attainable for delta greater than 1 and diameter greater than 1? So delta equals to 2. The graph are only the cycles of C2D minus 1. And for delta greater than 2, only 5 such graphs are known so far. Okay, so there are 2 non-isomorphic almost more graph. Oops, sorry. Okay, and for diameter greater than 3, there are no such graph for all even delta and many odds delta. Okay, so now this is the part that they try to reach the result from the upper bound, right? So you start with more graph, okay, this many exist, this the remaining are not, doesn't exist. So they go, how about 1 less, and then 2 less. Okay, and then as I told you in the beginning, there are 2 ways. Some people start by constructing from the lower bound, they construct, so how big I can get. Okay, so they do the lower bound. They try to construct the graph with given maximum degree and the diameter, then they try to see how big they can construct. Some people use the computer search, some use the algebraic voltage assignment, etc. And there is a Combinatorics wiki page that is dedicated to degree diameter problem. So if you look at it, there are a variant of the degree diameter problem. Okay, so here are the table that they have. So the red color, the red box, this red here, it means it's a more graph. So, or this is the optimal one that you cannot improve anymore. And these are the larger graph that they can construct. And also in the same web page, you can also see they compare it with the more graph, more bound, and they will tell you how far away it is from the largest graph. And if you look at it, there's still a lot of room of improvement. Like a lot of them are less than 50% of the bound. Okay.
Sorry, what are D and K, the diameter and degree? I'm not following the table.
So, okay, so sorry. So this is a difference. So K is the diameter in this case. Okay, and then D is the maximum degree. So the maximum degree is 3, and then the diameter 2, this is the Peterson graph. And this is where the Hoffman-Singleton graph lies. Does that answer the questions? Okay. All right, so the table is color coded by who found the graph. Okay, so if you're interested, you might want to construct your large graph, and so that you can pick your favorite color to put it here in the table. Okay, there's also another, this one we are talking about the undirected one, but they also have the directed versions, and they also have the mixed more graph. So there, if you are interested in more into directed graph than the undirected graph, at this wiki page, there are a lot of them. Okay, so you can see what people have done there. All right, so when we talk about the more graph, when we talk about the degree diameter, we allow any, so as long as it satisfies the maximum number of, sorry, the maximum degree, okay, we can have any maximum degree, and then we have any diameter, and then we try to construct what is the largest graph possible. Okay, so there's another variant of problems that we studied. So it's called the maximum degree diameter bounded subgraph. So it's abbreviated as MaxDDBS. It was introduced by Decker et al. In 2012. What is the difference of this is that right now we have a certain host graph, and then we try to find the largest subgraph that we can build given a degree and the diameter. But here, because it's a subgraph, then the maximum degree, it really depends on the host graph. Okay, so we have the host graph. We can take that it can go infinitely, but then the maximum degree normally is the one who bound. So we have an upper bound delta for the maximum degree as well, and then we also have the diameter, but then we try to find the largest connected subgraph lies inside the host. The order is given by and G delta D. Okay, so the order of the largest subgraph of G with given maximum degree delta and given diameter D. So what are the hosts? So here's an example, the mesh. So if you talk about the mesh as a host, then you can only have maximum degree 4. Like that's the maximum that you can have. So you either you find 4, 3, 2, that's it. So for the mesh of maximum degree 3 and you want the diameter 2, for example, this is the largest subgraph that you can get. Okay, you cannot add any more because it will make the diameter grows bigger. And here's an example of if you take maximum degree 4 and you want the diameter to be 5, this is the largest subgraph that you can get. Then this is the mesh studied by Mirka Miller, Ebert, and Zhou in 2012, also by Hashimoto. Then Shamek, Mirka, Ebert, and Zhou also did for honeycomb networks. They also do the triangular networks, and I studied the butterfly network and the Banus network, and also the hyperdiamond. Okay, so I will go through the Banus network, but Banus network is the back-to-back butterfly network. So I will first introduce what is a butterfly network, and then we can go to the Banus network. Here, okay, I will not talk about this definition that looks complicated. I will just I prefer to show you a picture. Okay, so butterfly network of dimension 1, and then this is a butterfly network of dimension 2, and this is a butterfly network of dimension 3. So then Banus network is 2R plus 1, has 2R plus 1 level, and this is a back-to-back butterfly, so it looks like this. So remember, this was the butterfly, that this is another copy of butterfly, so they join here. This is a Banus network of dimension 3. So you have 2 3-dimensional butterfly, you stack it together. Okay, so the way we approach the maximum degree diameter bounded subgraph is that first we try to study the host graph, look at it, how they connected, like the vertices. And then we try to see if we want a certain subgraph, what are the possibilities of the connection that we can have. Okay, and there is no general result that we have as in the degree diameter problem, because it really depends on the host, and different hosts behave differently. Okay, so for example, if we talk about, so the maximum degree here, if you can see that the maximum degree of the network, the host itself, is only 4. So when we talk about the subgraph, we consider the maximum degree 4, 3, and 2. So for the even diameter, we actually take the entire thing. Okay, if you want 4 and then even diameter, then you get this entire graph. Okay, and when you want the odd versions, you actually lost a lot of points. So from it's less than half of the network. This is the largest graph that we could construct. The approach that we do in this problem is the constructions. Okay, we try to find. And then when we talk about the maximum degree 3, we have the following constructions. Okay, this is for dimension 2, this is for dimension 3. When we first constructed this, sometimes we need a certain intuition. We have a feeling, oh, it has to be this big, and then we try to think how it's possible to have that many vertices in our graph. Okay, and for certain cases, for the odd cases, for the odd diameter, we constructed with the algorithm. So I can show you. So this is the graph of This is the graph of maximum degree 3 and then the diameter 7 in this case. Okay, so this is the algorithm. It's a bit complicated in the notation wise, but I can show you on the picture how it grows. So this is basically you start from the left and right, and then you join in the middle to create the graph. Okay, this can be done. This is for dimension 3, but you also can grow it for a larger dimension. Okay, from my experience working in these two butterfly and the bands network and also the hyperdiamond, they form a very nice pattern of generalization to go for a higher dimension. Okay. Then for the maximum degree 2, for the maximum degree 2, the largest cycle that we can get is the R2 to the power of R plus 1. The way we construct it, we just combine the two largest cycle that we can get from the butterfly network. And then this is about largest cycle that you can get in the butterfly network, 2 of them. And then we join them here so that we get the largest cycles in the bands network. So this is the largest cycle that we construct for the 3 dimension. And what's interesting, even though we are looking at the largest, we try to find the largest graph possible. But we also try to observe, in this case of the cycle, we try to see whether all the cycles of different length existed. Okay, for the cycles of the even length, it exists from 8 up to the largest cycle, except there is one cycle that is not there. So we still haven't been able to prove why this cycle is not there, because it has everything from 8 up to the biggest one. Okay, so this was a very interesting phenomena for us. Okay, now the other thing that is ongoing work is about the hyperdiamond. So I mentioned earlier there was a work of honeycombs. So honeycombs is the 2-dimensional. So we try to see this in terms of 3-dimensional. Okay, so if you look carefully, there is a honeycombs layer, and then they go 2 dimensions, to the 3 dimensions. Okay, so we try to construct the largest subgraph that we can have from this. So for the even diameter, the number of the largest subgraph that we could construct actually form a very nice sequence, and it's a crystal ball sequence for diamond, and it's also like this from the oeis.org. So plug in. So we work on the even diameter is done. So we are working on the odd diameter is done. We are working also to raise this to a higher dimension. What if we have more hyperdiamonds stuck together? Okay, so in order to find the subgraph in this case, we use a lot of inclusion exclusion, because we have so many layers. So we try not to double count things. So we do the inclusion exclusion to find the maximum order. Okay, so there are some improvement for the hyperdiamond, but we are not done with the work yet. Okay, so now the open problems is that, of course, is the more graph of degree 57 exists. Okay, this always remain open, and then we still have to prove the construction that we have for the maximum degree diameter subgraph. Are they the optimal one, or that bound actually can be improved? Okay, and for us, we need to construct the maximum subgraph of hyperdiamond with other maximum degrees. So right now we got the result for 4, maximum degree 4, and it can be improved. And you can also consider the other host graph. Okay, pick your favorite host graph and see what is the maximum subgraph you can construct. And then we also have, if we have two solutions, what is the best way to define the best subgraph? Okay, if you have, what is the better constructions? Okay, I think that's all from me today. Thank you for your attention. And these are the references. Okay.
Thank you, Novi.
Thank you.
So let's see, any questions for Novi?
Oh, I saw something on chat. Thank you, Brandon, for the links.
Yeah, I have a question.
Sure.
If I could ask a question. I noted when I saw you started out with the Peterson graph and the Hoffman-Singleton graph, and I was thinking that we were there's the intersection between the Moore graphs and the strongly regular graphs, but
yes.
Not every odd cycle is strongly regular, just the C5 or whatever. But I was just curious, does that come into play at all with some of this structure?
You mean this one, right?
Yeah, does the fact that they are strongly regular have anything to do with what we're talking about here? Just curious.
I don't work much in this area, like in that site, so I couldn't tell you much about that. But I can learn about it, and I will update you about it.
I'm just curious because there is the intersection there. That's what I was wondering. Okay, thank you.
Thank you.